this. So we talked about we talked about benzene, and we talked about its bromination reaction. Okay, there were two reactions that we had studied, which were, where are the two reactions? Just one second. That's Markovnikov's rule. I said this one. It started here. So there was one reaction that we talked about, which was bromination or chlorination, that needed a catalyst, FeBr3 or AlBr3. And we talked about the benzene electron cloud. You had, every carbon atom had a spare electron, and they were all overlapping with each other. A bromine molecule would not get polarized. There's going to be weak polarization because the pi electron cloud has low electron density. The electrons are very distributed. So the negative charge is not able to kind of repel the electrons over here. So this is not very strongly negative, and this is not very strongly positive. So the attraction for electrons is weak, which is why you need a catalyst. The electron cloud is pushing the electron from one side, and the Fe is attracting the electron from the other side. So Fe pulls the bromine, keeps it with it, and the Br that is positive, it goes and steals one of the electron in the p orbital and bonds with it. And the benzene pi electron cloud becomes electron deficient. There's a positive charge on it now. And that positive charge, it takes electrons back from H. And when it takes electrons back from H, H leaves, the electron cloud becomes complete again. There's no longer going to be this positive charge. So let me get rid of this positive charge just a second. I mean, this one would be, the positive charge would be gone because the benzene electron cloud is now going to get its electrons back because the H is left. This H has left, and the H plus 1 pulls the Br minus 1 back again and bonds with it to form HBr, and the catalyst is recovered. So the catalyst had played its role, and the benzene electron cloud is complete. So we did discuss this yesterday, and we talked about what are you going to write? What's the mechanism in the exam? I think we did write that somewhere. This one. So this is how you're going to state the mechanism in your exam. Benzene pushing the electrons away. Fe on the other hand trying to pull the electrons towards itself. And the same thing happens. You just show this, and that's it. So it's kind of the same mechanism, except you don't have to draw the whole electron cloud. You can just show it with a ring. That's it. Because it's very hard to actually draw the electron cloud. So you just show it with a ring. The ring becomes partial because the electron over here is gone. And then we talked about nitration, which was the addition of NO2 to a benzene ring. You need concentrated nitric acid, concentrated sulfuric acid, temperature is 55. And the step one is the production of the electrophile, and an NO2 plus electrophile is created. During a reaction, you have to remember this equation. And that NO2 plus 1 kind of does exactly the same things. It goes and pulls an electron from the benzene electron cloud. And the benzene electron cloud becomes electron deficient. So it pulls an electron back from H, and the H leaves. So NO2 takes its place and H leaves. That's it. So that is nitration of benzene. So those are the two main reactions for this. There are two more electrophilic substitution reactions whose mechanisms you should not be aware of. And we're going to discuss those quickly. So one of them, is the previous thing clear? All clear? Rubena, is this clear? Ethan?
Yes. Yes, sir.
So yep. Just remember these two mechanisms. The other ones, they're also electrophilic substitution. So that's known as, one of them is known as Friedel-Crafts alkylation, or simply alkylation, that's it. So using Friedel-Crafts alkylation, what you can do is you can attach a benzene ring to this. Okay, just hold on one second. Sorry, just a second. So Friedel-Crafts alkylation is that you basically attach a benzene ring, so you attach a carbon chain to this. You attach a carbon chain to benzene. And when you attach a carbon chain to benzene, what happens is the reaction is between a benzene. Let me just draw a benzene first. So ring, and you've got your so you've got your, is there a shape for a hexagon? Just a second. No. So anyway, so you no idea why I'm getting arrows. So just 1 second, forget this. As anyways, this is your benzene, and you're going to have a carbon chain. So let's say there's this really long carbon chain. It's got CH2, it's got CH3, and there's a Cl attached, and there's an H over here. Now the Cl is partial negative, and this H over here is going to be partial positive. This carbon over here is going to be partial positive. If it's partial positive, it's going to be attracted to the electrons in the benzene electron cloud, and the Cl electrons are going to they're going to be repelled further away. So it's kind of the same mechanism, but the mechanism is not required. I mean, what's going to happen is that this carbon atom, which was partial positive, it's going to come along and it's going to stick to this pi electron cloud. It's going to borrow an electron. Something similar would happen. You need a catalyst for this as well. There's going to be an AlCl3 catalyst or an FeCl3 catalyst that is going to be present. So we can, or FeCl3. The Al would, from the other side, try to pull the electron, so the Cl breaks off. So the whole point of the Al being there is that it would try and pull the Cl away from it. And if the Cl leaves, the carbon becomes positively charged. And in the next step, you're going to get something that's going to be very similar. That something similar would happen, and that is that this benzene over here, its electron cloud would become partial. It's going to lose its electron cloud. It's going to become partial because the carbocation that's formed, that's going to take that electron away from it. So the electron cloud is going to become partial because this particular carbocation that's being formed, it's going to come and stick to this. And it has two H's, and it's got a CH2 and it's got a CH3 as well. And there's an H as well. So it's exactly the same mechanism. The H, the benzene then pulls the electrons from the H to complete its electron cloud back again. So the next step would be that this molecule So the next step is going to be that this molecule is able to, the H then leaves and goes away, leaving its electrons back. And if the electrons are back, the electron cloud would become complete again. So the electron cloud becomes full again. And a carbon chain eventually bonds to it. So the mechanism is not needed. I just wanted to explain this, what's going on. So the mechanism is not needed, but it's kind of the same reaction. Just like electrophilic, this is electrophilic substitution. So it's exactly the same mechanism that's going on. So it's exactly the same mechanism. So a halogenoalkane is going to come along, carbon is going to be positive, and that particular carbon atom is going to stick to this carbon atom. That is something that you should be aware of. So if I draw this reaction, just the overall reaction, you should know in the carbon chain which particular carbon atom is the one that's going to stick to this benzene molecule. So for example, like if I take a benzene molecule, so here's a benzene molecule, and if I draw a reaction with this thing, let's say I've got a carbon chain, and this one has two H's, this one has a CH3, and you've got another CH3. And this carbon atom in the middle has a Cl. So if I do this reaction and I tell you that there's AlCl3 catalyst as well, and the reaction is going to happen. So there's this, so you have this AlCl3 catalyst going on. So you need to know, forget the mechanism, you need to know, or you should be aware of which of the carbon atoms is going to connect with the benzene. I mean, the whole chain would get attached, but it's going to be very specific. It's going to be this particular carbon atom. That's the one that's going to go, and it's going to get attracted to the benzene electron cloud, and that's the one that's going to connect with this. Is this point clear?
Yes, sir. Yes, sir.
Okay, बाकियों is this clear? Rubella, is this clear?
Yeah.
So because that's the carbon that's positive. That's the polar carbon atom. Adam, this is what we discussed over here, because all the other carbon atoms are non-polar. Like you've got a benzene electron cloud. Positive things get attached to the benzene electron cloud. So these carbon atoms are kind of non-polar. They don't have any polarity because carbon chains are non-polar. This carbon atom is polar because it's got a positive charge because it's attached to a Cl. Adam, is this clear? And the same is true over here. The other carbon atoms, they don't have any charges. This is the only carbon atom, that's the one that's polar. So it's this carbon atom that's going to connect with this benzene. So I'm going to do just that. I'm going to connect that carbon atom with this, and we can draw. So just think of this. This carbon atom is bonded to two CH3. So you've got a CH3. Yeah, you've got another CH3, and then there's a CH2. And another CH3. So this is going to be your product of the reaction, right? And there's going to be an HCl molecule that's going to be produced because one of the H is going to get substituted. That H is going to bond with the Cl that's leaving this carbon atom. So that's the molecule. That's the thing that you're going to get in this reaction. Now, the other one is we're done with electrophilic. This is alkylation. The other one is known as acylation. Okay, that's also kind of exactly the same thing. The mechanism is not important. Kind of something similar happens. So this one is Friedel-Crafts acylation. And in Friedel-Crafts acylation, so you have a benzene ring again. So this one is known as Friedel-Crafts acylation, or simply acylation. Now in this reaction, what happens is you've got an acyl chloride now. An acyl chloride is this thing. It's a CH3, a CH2, and it's got a C double bond O and a Cl. So remember, this is known as an acyl chloride. Something which has a double bond O and it's got a Cl next to it. So that's an acyl chloride. Now in this case as well, you've got this carbon atom that's very strongly positive, and you've got a Cl which is very strongly negative. So the electrons from the benzene are going to be attracted to this carbon atom. And the electrons of the Cl are going to leave. Eventually, they're going to leave. They're going to get knocked out. So, plus there's going to be a catalyst as well. In this case as well, it's going to be an AlCl3 catalyst. It would be pulling the electrons from the other side, but the mechanism is not required. So the only point you have to remember is that once this reaction happens, let's say this reaction is going on, you have an AlCl3 catalyst. So I'm going to drop the arrows. 1 second. Forget the mechanism. Just remember there's an AlCl3 catalyst that's involved over here as well. Remember who's going to bond with the benzene ring. It's going to be the carbon atom over here. So the benzene is going to come in. And this particular carbon atom, the one that I'm highlighting in green, that's the one that's going to come in and that's going to bond with it. That carbon atom has a double bond O on top of it. It's got a CH2 next to it. It's got another CH3 next to it. And again, it's also going to form an HCl molecule. That is what is going to, that is what's going to be formed in this reaction. Is this clear?
Yes, sir.
So just remember you've got Friedel-Crafts, alkylation, and acylation. Alkylation is with a halogenoalkane. That's it. It also has a positive carbon atom. You need a catalyst for that. And the positive carbon atom would go and stick with the benzene ring because the benzene ring has lots of electrons. Same mechanism as electrophilic substitution, but not required. And HCl is produced. So remember, the only thing you have to be careful about is that in the carbon chain, which is the carbon atom that's going to go and stick with this. So you have to draw the structure properly. In alkylation, kind of the same thing, except that it's now an acyl chloride, which has a carbon atom that has a slight positive charge. And AlCl3 catalyst is needed, and this carbon atom is going to go and stick with the benzene. And for this carbon atom, all the benzene carbon atoms are kind of identical. So it's going to stick with any one of them. They're all exactly identical. And an HCl molecule is going to be produced. So just remember, we're done with electrophilic substitution of benzene. And there are 4 reactions. 2 of them, no mechanism is needed. For nitration, remember, you'll be asked about the mechanism of the reaction. And for electrophilic substitution or bromination or chlorination, you will again be asked about the mechanism of this reaction. So is this all clear?
Yes, sir.
So Mohammed, Ethan, is this clear? Nabila, Zoha, is this clear?
Yes, sir.
Yes.
So just remember that apart from this, there's only one other mechanism left. We're going to do that. We're going to do that much later, but that's not related to benzene. This is the one that's related to benzene. Now, the next thing that we're going to study is something that's going to be very important, and it's going to define the properties of benzene. And we're still sticking to electrophilic substitution. Remember, we're still sticking to these 4 reactions. We're going to come back to these 4 reactions over and over again. This next thing is known as, I'm going to first give you the concept, because remember, it's not always going to be benzene. You've got lots of benzene derivative compounds. Which have benzene in them, but they've got other properties as well. So benzene derivative compounds, let's talk about them, and let's talk about their electrophilic substitution now. So first thing, need to remember what these benzene derivative compounds are. For example, let me just. So for example, I've got this benzene and I've got an OH. As the first one is, let's say we have got a carbon chain next to it. So we've got a CH2, CH3. or multiple carbon chains. I mean, this one would be called an arene. Okay, this one is going to be called, this is a propyl chain, alkyl chain next to a benzene. So this one would be given, you don't need to know the naming, like most benzene naming, it's not systematic. I mean, the nomenclature doesn't really cover benzene that much. So it doesn't have a systematic naming system. Most of the names are generic. So they don't have a systematic naming system. But this one would be called propyl benzene. So I'm going to do the simple ones. This one is a propyl benzene. It's got a carbon chain sticking out of it. Otherwise, you had these hydrogen atoms. Like if you look at the structure of benzene, where's the structure of benzene? This one. I mean, the first one over here. I mean, usually the benzene molecule is very symmetrical. It's got 6 hydrogen atoms sticking to it. But the one that I've drawn, instead of an H atom, there's a carbon chain that's attached on that side. So you got a carbon chain that's attached to this one. So this one is propyl benzene. You can have ethyl benzene as well, or methyl benzene. So we can have, let's talk about methyl benzene. I'm going to draw methyl benzene, and that's going to be this thing. I said then you might have 2 alkyl chains attached to it. TK, what do you do with that? That's let's say you've got a methyl and you've got another methyl. So you got 2 of them now. So let's say there's a methyl and there's another methyl that's taking over here. So this one is now a dimethyl benzene. Now the only thing is you have to give them at which positions are the carbons attached. So you always count from the closest side. Like this one is 1. So one of them is attached at position number 1. The other one is at position number 3. Okay, you always count the closest side, and it doesn't really matter. You give this one, it's going to be 1. This would be 2. This would be 3. So this one would be 1,3 dimethyl benzene, and we're going to just stick to this. We're not going to go into complicated namings because for benzene you don't have complicated naming. It's just you just start calling it something like toluene is something. Okay, if I just Google toluene, I mean, they don't call it methyl benzene even. They just call it toluene. Okay, so just remember they don't even use systematic naming for most benzene structures. So don't go into a lot of detail about naming. Just keep things simple. You've got an alkyl chain that's propyl. It's got 3 carbon atoms, so it's propyl benzene. This is methyl benzene. You got 2 methyl, that's dimethyl benzene, and that's pretty much about it. Even this one is not called methyl benzene. This one is called toluene. You just give it a different name altogether. No systematic nomenclature is usually followed. I said these molecules are known as arenes. Okay, so that's a benzene derivative. Kind of looks like benzene. It's almost like a benzene, but we'll discuss later that some of the properties are going to be different. Then there's going to be other compounds like phenols, which are benzene-related compounds or derivative compounds. So what's a phenol? A phenol is, take a benzene. In the previous case, you were sticking a carbon chain next to it, but now what we're going to do is we're going to have an OH group. So we have an OH group, which used to be an alcohol group, but remember, phenols are different from alcohols. They're not alcohols. They have some properties. I mean, this entire thing, it's not a benzene, it's not an alcohol, it's a phenol. A phenol is a separate functional group. So don't think of it as a benzene. I mean, it's going to be very similar to benzene, but it's not a benzene. It's going to be very similar to an alcohol, but it's not an alcohol. Okay, remember, this is a separate functional group that's known as a phenol. It's different from alcohol or benzene. Is this clear?
Yes, sir.
That's a phenol. That's a completely separate functional group. This entire thing. Similarities would exist, but it's going to be a different thing. You've got other things. You've got phenylamines. I mean, I'll do a few naming versions of this. So, for example, I've got this molecule, and I've got a carbon chain sticking to it as well. So I've got a carbon chain sticking. Now, OH, if you remember, OH has a higher precedence. Phenols have a higher precedence. So this one would be, it's a phenol. I mean, this part is a phenol. So you call it a phenol. The phenol group is going to have a higher precedence, 1, 2, 3. On the fourth carbon atom, there's an ethyl group sticking to it. So it's 4-ethyl phenol. Is this clear?
Yes, sir.
And there's another very popular molecule which we're going to study later on, and that's this one. You've got a phenol, and it's got bromine on this position, and on this position as well. So the OH is 1, bromine is 2, 3, 4, 5, and you got 6. So you got bromines. That's tribromophenol. I mean, it's a phenol with 3 bromines, and the bromine positions are 2, 4, and 6. So this one is 2,4,6 tribromophenol, which is a white precipitate, which we will discuss later. Because the OH has higher precedence. I mean, remember, even in the old naming in AS, the bromines were never given importance. You always counted from the functional group, which was OH. The double bonds had a higher precedence. The carboxylic acid had a higher precedence. The bromines never really had much importance. Okay? So we always give the smallest number to the OH group. Okay, Shafak, is this clear? I said then you've got that's phenols. Okay, that's phenols. Benzene with an OH, that's a phenol. And so then you've got phenylamines as well. Now, phenyl amines are basically benzenes with an amine group. Okay, so it's a benzene. So where's the benzene? Just a second. I'm just going to copy this. So it's a benzene with an NH2 group that's sticking out of it. So that's basically your phenylamine. That's it. And you can add things. There's going to be methyl phenylamine, etc., and so on. So just remember that's your phenylamine. You could have halogens attached to it. So, and we're going to just talk about chlorobenzenes. Like you can have chlorobenzene or bromobenzene. So in chlorobenzene, you're going to have a benzene with Cl sticking out of it. And remember that even these chlorobenzene are a separate class of, like halogenoalkanes. I mean, these are kind of different. Chlorobenzene are like a separate class of family of compounds. What else? You can have an aldehyde that would be known as benzaldehyde. So this one is going to be known as benzaldehyde. You can have benzene. Okay, just going to quickly cover this. Double bond O. So it's a benzene with an aldehyde. So this one is benzaldehyde. You've got benzoic acid. So benzoic acid is just benzene with a carboxylic acid. That's it. Okay, so you've got a carboxylic acid next to it. Okay, that's each one of them. Benzaldehyde is different. It's a completely, all of them are completely different molecules with different properties. Okay, all of them, the ones that I'm underlying, they're all completely different. You've got nitrobenzene as well. We just did nitrobenzene. We made one of them. So nitrobenzene is another one. Okay, so what's a nitrobenzene? It's benzene with an NO2 group. So that's about it. You've got all these types of structures. Don't go into we're not going to go into a lot more detail, just to give you an idea that we just studied benzene. Now we're going to talk about electrophilic substitution, and we're going to talk about the electrophilic substitution of these derivative compounds. Like what happens when you try and do electrophilic substitution for arenes or phenols or phenylamines or benzaldehydes or nitrobenzene or whatever benzoic acid, etc. So what's going to happen in that case? The mechanism, etc., would be kind of exactly the same. It's not going to be a different mechanism. It's the same electron cloud. So I'm going to group all of these derivative compounds that we just did, and I'm going to make two groups. One of them is going to be my 3,5 directing group. Let's start with a 2,4,6 directing group. So you've got 2,4,6 directing groups, and your 2,4,6 directing groups are these ones. Let's just start copying them. The 2,4,6 directing groups are, they're given in your data booklet as well. The first one, arenes. So I'm just going to copy that. I'm going to explain that in the next class. Which one is the 2,4,6 directing group? Like what does that even mean? The phenols are your 2,4,6 directing groups. So you got your phenols. What else? You've got phenylamines. Those are your 2,4,6 directing groups. And there's a whole list that's given in the data booklet. I'll just copy it from the data booklet just a second. Let me just, instead of copying it one by one. All of them are listed in your data booklet. So I'm just going to copy the relevant ones. There's somewhere in the data booklet at the end. Right at the end. You're given 2,4,6 directing groups, these ones. So let's just copy this thing. Forget this. I'm just going to copy this. So this one, that's already given in the data booklet. So if a benzene has an OH, it's got an amine like N with H atoms, amide as well. It's got a carbon chain, alkyl chain, or it's got a Cl. These are all 2,4,6 directing groups, or you can just call it 2,4. I'll explain what that means later on. And if the benzene is attached to NO2 with NH3, this should be +1. It's attached to a CN, it's attached to an aldehyde or a ketone, or it's attached to a carboxylic acid or an ester. That's a 3,5 directing group. So you've got all these different groups attached to benzene. And some of the groups behave differently, some of the groups behave differently as well. So we'll discuss this in a lot more detail in the next class. Okay. So I've just divided all the groups that are attached to benzene into two separate categories, and we're going to discuss what does that even mean. Okay. Is this clear? let's do this in the next class then. Okay, so that's we remember in the next class we'll discuss all of this, the 3 position direction and the 2, 4, 6 directing groups. So, everyone, take care.
Office.
Office.